doesn't understand language. So as long as I have a nice little baby time, she thinks she's silly.
All right. So yesterday we were discussing this shortcut to help us find derivatives called the power rule. Did we like yesterday? A lot better than the limits, right, that we've been doing. So we're going to continue kind of through the rest of this unit and even into the next unit of more shortcut techniques. Okay, we're going to be kind of little cheaters in here. Instead of using limits every single time, we're going to develop these shorter methods for us to use. So we're specifically going to take a look at trig functions today, just sine and cosine. Okay, nothing too crazy at first. But we're going to eventually develop the shortcut derivatives for sine and cosine. Now, in order to get to the shortcut, we are going to go through the long limit process, but this is the only time we're going to do it. Because once we know what the shortcut is, we won't have to use the limit process anymore. Okay? Now, in order for us to talk about derivatives of, or the slope of sine and cosine, we're going to need to use two identities that you may or may not have discussed last year. These are kind of the sum and difference identities. I'm not sure if these are going to look familiar or not. But if you are adding two different quantities or values inside of the cosine function, there is a particular way that you can break up those two values using an identity. Okay, this is not, I'm going to write this down, this is not cosine of A plus cosine of B. Okay, it's not like distribution. So I don't know if I'm doing a good thing by saying this or a bad thing by writing it down and having you guys see it, and sometimes when you see it you remember it. Okay, but this is a bad thing to remember. Okay, it's not distribution. The only way you can break up the A and the B is by using this identity. So specifically for cosine, we're going to take cosine of the A value times cosine of the B value and subtract sine of the A value times sine of the B value. This is what's called a sum identity, sum meaning addition. Notice how we're adding two things together in that cosine function. The sine identity is fairly similar, okay, but again, this is not sine of A plus sine of B. You don't distribute. It doesn't work that way, unfortunately. This would be sine of the A quantity times cosine of the B quantity plus sine of B times cosine of A. Okay, does this kind of look familiar from last year? Maybe, maybe not. Okay, so I see some yeses, some nos, that's okay. Alright, so we're going to have to use these two identities to help us find or figure out the shortcut derivatives for these trig functions. So we are going to have to go through the limit definition, but just this once. Okay, so let's go ahead and first check out sine. The limit as h approaches 0. Using our limit definition of the derivative, we would have to plug in x plus h into that x in the sine function. We then have to subtract f of x, which is just the original function that you're given. And that's all over h. Okay, so we're setting up the derivative using our limit definition. Okay, this doesn't change at all. It just depends on what it looks like based off the function. Okay, so let's keep going from here. We know that something should cancel out or at least disappear. Remember how we were able to cancel out a lot of terms and those h's for some of our other examples? Something similar should happen here. Okay, how might you want to rewrite sine of x plus h? Notice how you are adding two quantities or values inside of the sine function. Can we rewrite that somehow? It's not sine of x plus sine of h. You don't distribute. What do you want to try? Can we use, yeah, Vinny? Let's go ahead and use the second identity. Yep, we're adding two things. Now, this identity has A and B in it, but notice how we're dealing with X and H. Okay, but the same idea is going to apply. We're just going to have X's and H's instead of A's and B's. So this would be sine of X times cosine of H plus sine of H cosine of X minus sine of X all over H. Okay, so we used that sum identity for sine to break up the X and H quantity. Okay. Let's think about this. I'm going to reorder some things here, because you know when you're adding and subtracting things, you can kind of rearrange the way it looks as long as you carry the symbol, like the positive or negative, along with it. So I'm going to move this negative sine of X as the middle term. I'm just going to switch where these two are written. Is that okay with you guys? That's algebraically possible, right? You can reorder when you're adding and subtracting. So we're going to have sine of X cosine of H minus sine of X plus sine of H cosine of X. That's all over H. All right. Do we also notice how we have a single term denominator here, right? So couldn't we break up each individual numerator quantity over H? Okay. We're going to be a little strategic though in this one. Instead of breaking it up into 3 pieces, because we have 3 terms up top, we're going to just keep the first 2 together. You'll see why in a second. Okay, I'm going to just remind you guys again, I don't expect you to remember this, but this is the long way of figuring out the derivative, because this is eventually going to give us a shortcut. Are we okay with that process since we had a single term denominator? All right. Let's go ahead and just take a look at the first fraction that we have here. Do you notice how both terms up top have a sine x in common? Can't we factor that out? Okay, so we have a sine x, and then we would have cosine of H minus 1 all over H. Alright, let's see if we notice anything in here, okay? Notice how the H variable is going towards 0. Okay, that's kind of a key idea here that we're going to have to utilize. Do you notice anything special about how this first fraction is set up, or perhaps how this second fraction is set up? Do we know any special trig limits that when you approach 0, they have a particular value? Yeah.
Sine of C, well, sine of X over CX would give you 1, which in this case it's sine H over H.
There we go. All right. So instead of having X's, we have an H. Okay, that's just what the H variable is representing in the limit. Okay, that's our kind of variable of focus. And notice how the C's or the coefficients match, so that limit value should be 1. Do you see another one showing up? Can we do something similar in the other fraction? Yeah.
Cosine of H minus 1 over
There we go. This one goes to 0. Alright, so if we take a look, we essentially have sine of x times 0, which is just going to go away. And then we need to add 1 times cosine, which is just cosine. So it looks like, for our derivative shortcut, the derivative of sine, because that was our original function at the top, okay, the derivative of sine is cosine. So we're going to write that down here at the bottom. Okay, the derivative of sine is cosine. Mathematically, that's how it looks. Okay, so we're now just going to use this as a shortcut. Whenever I ask for the derivative of sine, you're automatically just going to say cosine. There's no need to go through that whole limit process that we just did, now that we know what the result will always be. Okay, so a nice derivative shortcut for sine in this case. We're going to go ahead and try the same thing for cosine. Okay, is it alright if I erase these little sections here so I have more room? Is that okay? Okay, let's try the same thing for cosine. So we have our limit definition of the derivative. We have to plug in x plus h into the original function minus the original function all over h. I'm glad there's a breeze outside, but I wish it was cooler. Okay. All right, where do you guys want to go from there? Can we rewrite cosine of x plus h? Good, Ariana? There we go. Yep, so instead of a's and b's, we're going to use the x and h. So we have cosine of x times cosine of h minus sine of x times sine of h. We also need to keep the minus cosine x from the original derivative and all over h. All right, kind of similar process here. I'm going to switch the order of those two terms. Doesn't really matter algebraically. You're just reordering it, or how it looks is just a little different. Again, we have a single term denominator, so we could probably break up each numerator piece. But again, instead of having 3 individual pieces, it might be a little bit more strategic for us to keep the first 2 together. Notice how in the first fraction they both have a cosine x in common, so we can factor that out. And we're left with a cosine of h minus 1. Really isn't anything we can do to the second fraction. Alright, so something should be happening here that's going to allow us to cancel or get rid of some things. Can we see those trig limits showing up again? Okay, so cosine of h minus 1 all over h goes towards 0. Sine of h over h goes towards 1. So it looks like we're left with cosine of x times 0, which is just going to go away. And then we have to subtract sine of x times 1, which would just leave us with a negative sine of x since we were subtracting. So there's our derivative shortcut for cosine. Okay, no need to go through the long, tedious limit definition. whenever we come across the derivative of cosine, we just have to remember or know as our shortcut that it's negative sine of x. Okay, so in addition to the power rule we discussed yesterday, because we're going to do a little bit more with that today, we need to know these two other derivative shortcuts. Okay, they're kind of similar, so they can be confusing, but we need to know the difference between the two. Okay, so let's give some of these a shot. We're going to have some more power rule examples, maybe some trig thrown in here. Let's see how we do. So we're going to go ahead and find the, let's see, for each of the following, find the equation of the tangent line at the given point. Okay. What information do we need to know to write the equation of any line? Yeah.
Slope and a point.
A slope and a point. Okay, so let's go ahead and write that down. Slope and a point. Okay. When I say slope, you think derivative. Okay, so the slope of the equation is going to come from the derivative, whereas the point value comes from where? Point value, aka y value, aka height. Where might the point come from? Yeah. The original, or f of x, whatever it's named. Okay, so we'll say original. Okay, so we have to know an original equation, which we do in all these cases, but we also have to know the derivative equation, okay, the slope at any point. So let's go ahead and try to tackle maybe first finding the derivative of our equation here. What do you guys feel like doing? Do you guys want to use the long, tedious limit process? Ryan's all game. No? No? All right. So let's try to use a shortcut perhaps. What do you feel like doing for this one? Let's expand it, okay? So we'll do some distribution, okay? We need to get it into polynomial form. We need x's to powers, okay, in order to use our power rule, meaning no fractions, no parentheses, nothing like that. So if we were to expand x plus 1 squared, okay, write it twice and go through a FOIL process, we'd have x squared plus 2x plus 1. But then we still have parentheses, so we have to go through another distribution process here. Kind of tedious, but worth it in the end. We'd have, let's see, 2x cubed plus 4x squared plus 2x minus x squared minus 2x minus 1. So combining like terms, okay, that's still our original function. Okay, we didn't use any derivative shortcut. We just rewrote the way it looked. So if that's the original, okay, f of x, let's go ahead and find the derivative, f prime of x, that little apostrophe. Can we use the power rule from yesterday really quickly? Are we that good at it so far? We got 6x squared plus 6x, right? Good. All right. So notice how we have our two pieces. We have a derivative equation to help us out, and we have an original equation to help us out. We're going to use both of those to help us figure out the slope and the point. Okay, so let's figure out the slope first. We specifically want the tangent line, okay, the line that touches the graph at only one point, specifically at the x location of -1. So we're going to plug -1 into the derivative to get the slope value at that point, at that location. And we'll plug in -1 into the original equation to get the height, or the y value, at that location. All right, so if we plug in -1 into the derivative, we'll get 6 minus 6 which is 0. And if we plug -1 into the original equation, okay, either the way it was written at the very top or into how you expanded it, it really doesn't matter because they should both represent the same y value. Are we going to get 0 for that one too? Okay, so equation, we have y minus 0, which was our point value, equals the other 0, which is the slope, times x plus 1. Okay, you can leave your answer just like that. If you wanted to rewrite it in slope-intercept form, okay, you could do that too. Completely up to you. Is that okay? Do we want to leave it like that? Is point slope kind of becoming our friend? Nice and easy? Alright, let's go ahead and try the next one. We're going to write another equation of a tangent line. We got to figure out the slope and the point. Let's go ahead and figure out the derivative, though, to help us with the slope value. There's no way we can rewrite what's going on in here. There aren't any parentheses we can expand. There aren't any fractions that we have to worry about. So we should be able to go through this one, okay, fairly simply. Let's see, we have 4 times sine of theta. Okay, if you don't like thetas, you can think about them as x's. What is the derivative of sine? Do you remember our shortcut? The derivative of sine is, yeah, cosine. Okay, so what do you think the derivative of 4 sine is?
4 cosine?
4 cosine, yep. Don't overthink it. All right. What about then the derivative of theta? Or in other words, the derivative of just x, if you thought about it that way. Yeah.
It would just be that number? Like, it would be a constant. So
It would be a constant.
-1.
-1. Okay, you can think about this as minus x if you wanted to. Okay, and use the power rule on that. You would bring down the power of 1, and then you wouldn't have any power left. So you're just left with that number. Okay, so there's our derivative. That's representing the slope at any point. Let's go ahead now and figure out those slope and point values to write our equation. So our particular tangent location here is pi over 2. We're going to have to plug in pi over 2 into the derivative as well as the original. Alright, so unit circle time, pi over 2 is a location we have to know. If we plug in pi over 2 into the derivative, okay, we would have cosine of pi over 2, which is 0, right? Pi over 2 is the very top spot. Okay, so 4 times 0 is 0, minus 1 would leave us with a -1. Let's go ahead and plug in pi over 2 now into the original equation. We would have sine of pi over 2. What's the sine value at the very top point? 1. Okay, so we have 4 times 1, which is 4. And then we would have to subtract pi over 2. Alright, so let's go ahead and write our equation. It's going to look a little weird because we don't necessarily have a calculator to maybe simplify this. Let's say we didn't have a calculator. So we would need y minus, okay, the point or y value. So you need to subtract the entire quantity. You can either represent that in parentheses. Maybe some of you would want to distribute that minus sign through, completely up to you. So we have y minus y1 equals our slope times x minus x1, which is our pi over 2 value. We doing okay? Do you guys think you can tackle the next one? Another trig one? Maybe try it? See how far you get? We'll work it out together. How'd it go?
I mean, it happened.
It happened?
I don't want to say I did good, because then I'll do bad, but if I say I do bad, then I'll do bad. So, yeah, it happened.
It is what it is. Yep, it happened.
Yeah.
C'est la vie, right?
Yeah, exactly. Thank you.
Uh-huh. Yeah.
This one's just.
How'd it go? How'd it go?
Pretty good.
All right. Any takers on the derivative using our shortcuts? Let's take it slow. The derivative of 2 theta, or just 2x if you want to think about it that way. Just 2, okay? What about the derivative of 3 cosine? Yeah.
3 negative sine theta.
Okay, so we'll say -3 sine theta. That's fine. Yep. Good, good, good. Okay, so now we can figure out the slope and the point because we have our tangent location at pi. If we were to plug in pi into our derivative to get our slope, let's see, sine of pi, unit circle, furthest left point. Yeah. 0. So we have 2 minus 0, which would just be 2. Let's go ahead and plug in pi into the original to get our point or y value. So we would have a 2 pi and then plus 3 cosine of pi. So furthest left point, what's the cosine value? Yeah.
-1.
Good. All right. -1 times 3, we'll have a -3. So we got to put those two values together to write our equation. Y minus the y point equals our slope times x minus our tangent location. How'd you guys do? Really good. I like the head nods. All right, let's check out the next one together because this one can be a little tricky. If we're going to use the power rule, we're going to have to make sure that there's no fractions and everything is written as x to a power. No trig in this one, okay, so we don't have to worry about that. How might you want to rewrite the original function? Somehow we got to rewrite the root, and we're going to have to rewrite the fraction. Let's try the root first. How can we rewrite the square root of x cubed? We briefly went over this yesterday. Maybe look back at the other two examples we did. What do you think, Braden?
X to the 1/3.
X to the what?
1/3.
Not 1/3.
2/3.
Other way. 3 halves. All right. The denominator represents the root. The numerator represents the power. We have a square root, aka a root of 2, and the power on the x was 3. Okay, so that's nice because now we have x to a power, but now we also have to get rid of the fraction or division somehow. So, where do you guys want to go from there? When you are dividing the same base, what can you do to the powers? X to the first, x to the 3/2. You can subtract them, right? So 1 minus 3/2 or 1 minus 1/2 would be a negative 1/2. And we still have that coefficient of 2. Alright, so there's our original function rewritten. Notice how we have x to a power. Okay, no more roots, no more fractions. So we should be able to figure out the derivative using our power rule. So let's see, that would be negative x, and if we subtract 1 from the power, that would be a negative 3/2. There's a lot of negatives going on in that derivative. Let's try to clean it up a bit. If you have a negative exponent, you can move it to the bottom to make it positive. We would still have the negative sign though up top, so we need a placeholder of -1. And if you wanted to, you could change back that 3/2 power. We would need a square root, because the denominator is 2, and an x to the 3rd on the inside. So maybe we'll use that as our cleaned up derivative. So let's check out the slope and the point to help us write our tangent line. We're specifically having a tangent location at 2. So if we were to plug in 2 into the derivative, let's see, 2 cubed would be 8. So -1 over the square root of 8. You can leave it like that, by the way. Okay, the AP people don't make you rationalize, like get rid of a square root in the denominator. You can leave it like that. Okay? If we were to plug in 2 into the original, we would have 4 up top and then another square root of 8 on the bottom. You can leave it like that. Technically, it would simplify a little further if you wanted to rationalize it, but you could leave it. So now that we have the point and the slope, we'll write our equation. Y minus the point equals our slope times x minus the tangent location, aka our x value. We're starting to get the hang of these a little bit. We're going to keep doing these all year. We're going to get really good. All right. So let's go ahead and take a look at how these derivatives might represent different graphical characteristics, because that's going to kind of lead us into the next section tomorrow. Given the equation of a function, how might you determine the values at which a function has a horizontal tangent line? AKA, if you were to plot a point and draw a tangent line, it would be horizontal, aka flat. Okay, so let's take a look at what this phrase might mean, because horizontal tangent, I'm going to tell you right now, is going to show up a lot. If you have a horizontal tangent line, what is the slope of a horizontal tangent line? Yeah.
0.
0. All right, so the derivative would have a value of 0. And graphically speaking, if you have a derivative or a slope of 0, do we know what possibly is happening on the graph at that spot where it has a slope of 0? Can you describe what the graph might look like? Yeah.
The max or min.
You have a max or a min. Okay, so if you think about all those polynomial kind of curvy graphs that we looked at, if I draw a tangent line somewhere here, okay, that's not a slope of 0, that's a positive slope. If I draw one on this side, that would be a negative slope. The only way you have a horizontal tangent line is kind of at a maximum or a minimum. Okay, so we'll say we have a possible max or min. So whenever you're finding those horizontal tangent locations, you are finding possible spots of a maximum or a min, a high point or a low point. So let's try to investigate this idea when we apply it to a problem. Okay, so for what values of x would this function have a horizontal tangent, aka a derivative that equals 0, a slope that is 0? Can we figure out the derivative of that function? Real quick, right? Now that we know the power rule. Okay. Derivative would be 3x squared plus 1. So how can we kind of merge these two ideas together? Now that we know what the derivative equation is, and we specifically want a derivative, aka slope of 0, can we bring those two ideas together? What do you feel like doing? How can we merge these two? Yeah. Set the derivative equal to 0. So we know the derivative is 3x squared plus 1. Let's go ahead and set it equal to 0. We want to figure out when the slope or derivative is 0. Alright, so let's go ahead and solve for x. We can subtract 1, divide the 3. Square root both sides. So it'd be plus or minus the square root of negative 1/3. What do you think that's telling you? What is the square root of negative 1/3? Yeah. Imaginary. Alright, so that means there are no solutions. Okay, it's not possible to figure out a specific x location. No solutions. So let's go ahead and maybe formally answer this question. At which x values would you have a horizontal tangent? We specifically saw that there are no solutions to this question, so therefore there are no x values. There are no x values where we'll say f prime of x, the derivative is 0. So what's that telling you graphically about this original function? If there's not a single spot where you can draw a horizontal tangent line, what's going on with the graph? If there's none of this, then what? Does it make sense that there's none of those? Okay, so if there's no location where you have a horizontal tangent line, that must mean there's no max or min on the graph. So we'll say, so there are no max/min on the graph of f of x. Okay, that original function. So there's no high point or low point. Okay, let's check out another one. Maybe we'll do a trig one. Okay, what values of theta, okay, if you don't like theta, you can think about x, does this function have a horizontal tangent, aka the derivative is 0? All right, so let's go ahead and find the derivative of our function. We should be able to do that real quick now that we have some of these shortcuts. The derivative of theta using our power rule, aka the derivative of x if you did it that way. Just be 1. And then what's our derivative shortcut for sine? The derivative of sine is cosine. Okay. So we want to figure out where we have horizontal tangent lines, aka slopes of 0. So we'll substitute in 0 for the derivative location. Let's go ahead and solve for theta. That's our variable in this case. So we'll subtract the 1 over. All right, so without a calculator, you got to think about your unit circle. Where, okay, what radian location, where on the unit circle does cosine have a value of -1? Can you think about that radian? Yeah, pi. Good. That's the only location. Sometimes there's 2. Those are the tricky ones, but in this case, that's the only one. Okay, so we'll say if this is a location where there's a max or a min, we could say there is a possible max or min at the theta value of pi, because we have a horizontal tangent. We don't know which one it is. We don't know if it's a high point or a low point. Okay, we'd have to do a little bit more analysis to figure that out, and we're actually going to get into that in a few sections. Okay, but at least for now, we know that there's one, possibly one of them, at that location. Does that make sense? Horizontal tangent, slope of 0, right? Horizontal line has a slope of 0. Perfect. All right. That's it for this section. I know the bell's going to ring in a little bit, and I meant to ask at the beginning of the period, so I'm sorry. But are there any homework problems that you guys want to go over in the remaining time that we have? If you had a chance to look at some of them from the other sections? No? All right.